Okay, so molecular geometry looks at the three-dimensional arrangement of atoms in a molecule. So a lot of times, like when we've been drawing water, it just shows up like this in a nice straight fashion. However, that's not true of what it actually looks like. So it's important because the same influences chemical, or the shape influences chemical and physical properties of that chemical, such as melting and boiling points, solubility, density, and the type of reactions in which it can do. So basically this section will show you where, like, why this is more correct than putting the hydrogens on top. Does that make sense? Where we've said that there was a little leeway in your diagrams before. Now this section will kind of iron out those nuances, I guess. So we've talked about the valence shell of electrons, but just as a reminder, it is the outermost occupied shell of electrons in an atom. And we get this wonderful theory and model and idea that's the valence shell electron pair repulsion model. Thankfully, they call it VSEPR for short. States that a molecule will adjust its shape so that the valence electron pairs stay as far apart from each other as possible. This is because like charges repel each other. The number of bonding pairs of electrons and lone pairs around the central atom also influence the shape. Double bonds and triple bonds, in terms of electron repulsion, are no different than a single bond. Only though when we talk about electron repulsion. A double bond doesn't repel electrons more than a single bond does. They repel them equally.
Well, now you're talking.
So the first structure that we are going to look at is when the central atom has no lone pairs. So when we look at these, we're going to have a general format to the equations. So A represents a central atom, and B will represent the atoms that surround that central atom. So generally speaking, atoms or central atoms with no lone pairs of electrons will have this format, AB2. An example of this would be beryllium hydride. And then we see that we have a perfect linear geometry. And then the bond angle, so the angle right here, or here in this particular one, or over here, each of those bond angles are 180 degrees. Makes sense. A line has 180 degrees. So our next structure would be when we have the general form AB3 and have that central atom surrounded by three other atoms like boron trifluoride. We get a geometry that we call trigonal planar. And our bond angles will be 120 degrees. With trigonal planar, all four atoms, 1, 2, 3, and 4, all of them lay on the same plane. So if you were to place that molecule on a piece of paper, it would lay flat. There would be no molecules sticking up off that paper or down below. It sits perfectly flat on the paper. AB4, like methane, the atoms will not lay on the same plane, and one atom will shoot up or down, and this maximizes the distance between all four of the hydrogen atoms. This shape is referred to as tetrahedron. Sometimes it's also called tetrahedral. Same thing. And your bond angle here is 109.5 degrees. Sometimes in your textbook, the way they might show this drawing is like this structure, where two of the bonds will be shown like normal lines, and then two adjacent, one will be like a solid triangle and one will be dashes. That indicates that one of those is angled downwards and one of them is angled upwards. So it doesn't matter really which one is which. It's just a way to try and show that it's in 3 dimensions. All right, our next structure will be trigonal bipyramidal. And our bond angle is 120 degrees. In this particular situation, we have something called equatorial atoms. And equatorial atoms are the ones that lay on the flat plane, like an equator. Then we have our axial atoms, which are the atoms that are perpendicular-ish from the equator. Your bond angle between the phosphorus and then a chlorine axial atom will be 90 degrees. Not the 120. All right, next structure is AB6, like sulfur hexafluoride. This shape is called octahedral. And it has a bond angle of 90 degrees. So what happens if we have one or more lone pairs of atoms? This is when we start to look at the electron domain geometry. And this looks at the total number of electron pairs, whether they're bonding or just lone pairs. So an example here would be AB2E, and the E stands for lone pairs. And so ozone, which is O3, has one set of lone pair atoms on that central oxygen. And so the lone pairs of electrons are slightly more repulsive than bonding pairs of electrons, meaning they take up more space. And so it's going to so your lone pairs are up here. And what it's going to do is it's going to push this bond and this bond as far away from that lone pair as possible. So we're going to get this bent structure to it. So we have these handy dandy tables that take a look at the total number of electron pairs, the number of bonding pairs, how many lone pairs of electrons. If you know that information, meaning you've sketched out your Lewis dot structure, you should be able to determine the electron geometry, the molecular geometry, and this last column just simply gives you examples. So if you have 2 bonding pairs and 2 lone pairs, you get the electron domain geometry as tetrahedral, molecular geometry is bent. So when you're doing the assignment for these problems, or the problems surrounding this, you have to make sure you're paying attention to whether it's asking for the electron domain geometry, the molecular geometry, or it could ask you for both. So then this last slide here just kind of summarizes it when there is no lone pairs. So this is all kind of like that AB2 or AB3 that we first looked at in this set of notes.